Hi class, this is Mrs. Brunk. In this unit we're going to be reviewing some exponent rules. So almost everything in this lesson should be review. We're going to be looking at things like zero and integer exponents. We're going to be looking at multiplication properties of exponents and division properties of exponents. And we're even going to be looking at rational exponents or fractional exponents. And these are all things that we studied earlier in this course and also in other courses such as Algebra 1. So we'll start out by looking at integer exponents. And we're specifically going to be looking at the integers 0 and negative integers. So recall, any non-zero number that is raised to the 0 power is always equal to 1. So we could be raising a positive number to the 0 power, like 3 to the 0, and we get 1. We could be raising a negative number, like negative 16 to the 0 power. We could be raising a fraction to the 0 power, and we could even be raising a variable to the 0 power. And as long as the base that we're raising to the power is not 0, then the value of that will always be 1. So anything except for 0 raised to the 0 power will always be 1. And secondly, a negative exponent. A non-zero number raised to a negative exponent is equal to 1 divided by that number raised to the opposite exponent. So really, actually, it's what it's saying is the reciprocal of the base raised to the positive power. So really, when you see a negative on an exponent, it means take the reciprocal of this base to the positive power. So for example, if we raise 3 to the negative 2 power, as shown here, that's equal to 1 over 3 squared, which is 1/9. Or 2 to the negative 4th power is 1 over 2 to the 4th power, which is 1/16. So let's take a look at a few examples of 0 and negative exponent integer powers. So example A, 4 to the negative 3 power, what that really means is 1 over 4 to the 3rd. And hopefully we know that 4 to the 3rd power is 64, so that's really 1/64th. 7 to the 0 power, of course, is it's a non-zero base, so anything raised to the 0 power will be 1. Negative 5 raised to the negative 4th power, what that really means is 1 over negative 5 raised to the positive 4 power. So again, that negative on the exponent really just means the reciprocal, or 1 over that base to the positive power. And so that would really be 1 over negative 5 to the 4th is 625. So that'd be 1/625th. Now the difference between C and D is that there are no parentheses around the negative and the 5 to group them together. So what that really means is the opposite of 1 over 5 to the 4th power. And so that opposite out in front is going to take whatever we get when we raise that base to the power and take the opposite of it. So that's going to give us 1 over 625, and the opposite of that would be negative. So negative 1/625th. Okay, so how about if we are evaluating expressions with these different types of exponents on them, 0 and negative exponents. So for instance, x to the negative 2 power, if x is 4, really just means the same as saying 4 to the negative 2 power. And that's just really the same as 1 over 4 squared, which is 1/16th. So let's go ahead and do this next example as a you-try question. So we're going to label this a UTQ, and when we do you-try questions, the expectation is that you're going to pause the video and you're going to give those a try. And usually when you turn back in, I'll go over the answers. Sometimes I won't. Sometimes I'll have you, we'll talk about those when we meet in class. And sometimes we'll just reserve certain questions and we'll say these will be you-tries for in class. But we're going to go ahead and make this a you-try question for right now during the video. So if you'll pause the video now and give this one a shot and then tune back in to see how you did. Okay, so the final answer for that expression should be 2. So let's go ahead and turn the page. Now this next grouping of questions, we're going to go ahead and designate these as in-class you try questions, and these will give us a chance for you to kind of think back on the lesson and try to apply this when we're together in class, so that if you are struggling with any of these concepts so far, that you'll have a chance to ask some questions and get some assistance. So we're just going to move on and talk about the multiplication properties of exponents. Now you may remember the product of powers property. It basically says the product of two powers with the same base is equal to that base raised to the sum of the two exponents. So for instance, if we were multiplying 6 to the 7th times 6 to the 4th, that's really the same as saying 6 to the 7 plus 4 or 6 to the 11th power. And this works also for variables as shown in this example here. So in general, when the two bases are the same and you're multiplying them, you simply have to add the exponents. Let's take a look at an example. So we're asked to simplify. So remember the key to what that property said was that we had to have the same base. So we have a couple common bases here. We have two terms that have q as the base. So that means I can combine them and by adding the exponents. So that'll be q to the 3 plus 6 or q to the 9th power. And since then there's not anything I can group the r squared with, it just remains as r squared. So my answer would be q to the 9th times r squared. Now what about example B? Well, this is where I see some students make some mistakes in the past, and that's because sometimes when you have a base that does not have an exponent listed on it, they forget that that's really implied that it's really a 1. So what this is really doing is combining these three bases that are all the same, and to do that we're just going to add the exponents. So this will be n to the, well, let's see, 3 plus 1 is 4 plus negative 4 is 0. So these exponents actually add to 0, which then we can apply the 0 power product property, which says that anything except for 0 raised to the 0 is 1. And so our answer here would be 1. Okay, how about the power of a power property? So remember, with the power of a power property, you have a single base that's being raised to two different powers. So a power raised to another power equals that base raised to the product of the exponents. So in other words, we take those two exponents and we multiply them. So for instance, 6 to the 7th power raised to the 4th would be 6 to the 7 times 4, or 6 to the 28th power. And again, this works also for variables, and in general, a to the m to the n power is equal to a to the m times n power. So when we have a single base raised to two powers, we multiply the exponents. Let's turn the page and take a look at applying that property. Okay, so power of a power property. Example A, x to the 3rd raised to the 4th would be x to the 3 times 4, or x to the 12th power. In example B, 6 to the 0 to the 3 power. Well, really remember that 6 to the 0 power is actually is 1, and 1 to the 3rd power is 1. Now we would have gotten the same thing if we had just simply done it like this. 6 to the 0 times 3, 0 times 3 is 0, so that'd be 6 to the 0 power, which would give us 1. So either way that you look at it, the final value of that power is 1. Now how about we do C as a U-try? So this U-try question is going to combine the last two properties that we learned. And so if you'll pause the video now, give that one a try and tune back in, and we'll take a look and see how you did. All right, so in this example, we got to apply the power of a power property in order to raise x to the 3rd to the negative 5th power. Then the product of powers property at this level right here, because we had two bases that were the same, so we had to add the exponents. And then finally, when we added the exponents, we ended up with a negative exponent, so we were able to apply the negative exponent property to rewrite this without a negative exponent as 1 over x to the 11th. Okay, how about another property? So how about a power of a product property? Now these properties are starting to all sound alike, but the difference here is the order of things. So this time I'm saying the power of a product property. In other words, I'm raising a product, which means two or more things being multiplied, and I'm raising it to a power. So what does that property say? A product raised to a power equals the product of each factor raised to that power. In other words, basically, if we have a product being raised to a power, then we sort of have to distribute, if you will, that power to each thing in the product. So, for instance, if we had 2 times 4 being raised to the third power, that's the same as saying 2 to the third times 4 to the third. And then, of course, we know that 2 to the third is 8, and 4 to the third is 64. We would then finally multiply those two things together to get the final answer of 512. And this works whether we're working with variables being raised to these powers, or if we're using just numbers, or if we have combinations of numbers and variables. So when you raise a product to a power, that means each thing in the product gets the power. So looking at example A here, we have the opposite of. Now I read that opposite of when it's out in front of the parentheses. Otherwise, if it had been inside out, I would have read that as negative 2y being raised to the second power. But so it's actually saying take the opposite of 2y raised to the second. So the things that are going to get this exponent of 2 are going to be the 2 and the y. Now that negative, which is out in front, it's not grouped with the negative 2y in the parentheses, so it's just saying take the opposite of whatever I get. And so when I raise 2 to the second power, and y to the second power, well, 2 to the second power is 4, and then y squared is, of course, just y squared. And so our final answer would be negative 4y squared, or the opposite of 4y squared. So other than the exponent being 3 in example B, the big difference here is that, notice this time, the negative is inside the parenthesis. And that means that that 3 is applying to that negative 2, not just the 2, but to the whole negative 2. So what that really means is I'm raising negative 2 to the third power and then y to the third power. Negative 2 to the third power would be negative 2 multiplied by itself 3 times. That's negative 8 and then y cubed. Okay, time to turn the page. Okay, so the main focus of the next couple of properties we're going to be looking at are going to be, it's going to be revolving around division, or what we call quotients. Now the first property is called the quotient of powers property. Now the quotient of powers property arises when we are dividing two bases that are the same, that are being raised to powers. So what that says is the quotient, in other words, the result of a division, of two non-zero powers with the same base, that's again important, we have to have the same base, will equal the base raised to the difference of the exponents. So in other words, we're going to subtract the exponents. Difference means subtract. So take a look at our numeric example. 6 to the 7th divided by 6 to the 4th would be 6 to the 7 minus 4 power, or 6 cubed. Now if you kind of think back and remember why this worked, because 6 to the 7th would mean this, or 7 sixes being multiplied, and 6 to the 4th would mean this. And so when you're dividing this, you can kind of think about just doing canceling, cross-canceling. Cancel something on the top with the same thing on the bottom. And so if we did that all down the line here, what we'd be left with on the top is just 3 sixes being multiplied. And so that sort of verifies where that property comes from. And as usual, here's this generalization with variables, sort of like the rule in, symbolic representation of the rule. And of course, most important thing, let's actually apply that property. So if we had x to the 4th divided by x to the 3rd, that would be the same as x to the 4 minus 3. Because basically we could just cancel all 3 of these on the bottom, leaving us only 1 left on the top. So x to the 1st. Now, it's really helpful to think about the idea of canceling when we have something like b, where, say, the higher power is actually on the bottom. So instead of thinking about really just subtracting the exponents, and this would really be the same as, since the exponent on the top would be subtracting 4 from 1, which would then give us a negative exponent, which, remember, it's not okay to leave a negative exponent. We always want to switch it to a positive exponent by applying that negative exponent property. So really the easiest thing to do in this kind of situation is to really do just thinking about, this is like canceling. So if I had one y on the top, I could cancel one of the y's on the bottom. That leaves 3 on the bottom, and that would give me a result of just a 1 left on the top because I canceled the 1 out, and a y to the third on the bottom. And so that just sort of leaves that step off at the end where we would have to apply that negative exponent property. And then in something like C, it gets even more important. So now we have things like numbers that are being divided. We have variables that are different bases being divided. And so being able to kind of split them up in this way, and then thinking about the whole canceling out top to bottom really is very helpful here. So for instance, with the numbers, I could cancel a 3 out of both the numerator and the denominator. If I cancel it out of the bottom, I have 1 left. Out of the top, I have 5 left. With the variables x, if I cancel 2 of the x's on the top, there's only 1 left on the bottom. And if I cancel the 2 y's on the bottom, that's going to leave me with 1 y on the top. And so that final answer would look like this. On the top I have a 5. Here there was just a 1 left when I canceled out the 2 x's. And so that left me with 5 times 1 times y to the first, which is 5y. And on the bottom I have 1 times x to the first times 1. That's really a 1 here, which is really just an x to the first, or an x. And so my final result of dividing 15x squared y cubed by 5x cubed y squared is simply 5y over x. Oops, and I just noticed I made an error right here. When I rewrote the problem, I rewrote that as a 3, and it should have been a 5. I apologize for that. And that, of course, is going to change this on the top to being, instead of what it was before, I now can see that it's just a 3 because I could cancel out a 5 out of the top and the bottom, which would leave me a 3 on the top. So sorry about that. Hope that didn't confuse you too much. Now what about the positive power of a quotient property? So a quotient being raised to a positive power equals the quotient of each base raised to that power. In other words, if we have a quotient, you can simply, again, sort of, if you will, distribute the exponent to the top and to the bottom. And that's a way to simplify it. Now, the reason why this works is if I was raising something like 3/5 to the 4th power, that's like multiplying 3/5 times itself 4 times, which then gives us, in the numerator, 3 multiplied by itself 4 times, and on the bottom 5 multiplied by itself 4 times, which is the same as saying 3 to the 4th over 5 to the 4th. And so essentially what we do, if we have a quotient, we can just apply that power to the numerator and the denominator. And of course the symbolic rule here, a over b to the n power is a to the n over b to the n. And let's take a look at applying that property. So I have the quotient 3/2 raised to the 2nd power, and so that's really the same as saying 3 squared and 2 squared. 3 squared is 9 and 2 squared is 4, so that's really the same as 9/4. So how about a you try question for B? Thank God, this one seems easy enough. So go ahead and pause the video and try example B and tune back in to check your answer. And your answer should have been x to the 4th over y squared. So in this question, you got to apply both the power of a power property and the power of a quotient property as well. Let's go ahead and turn the page. And I guess sort of like a version B of that that power of a quotient property would be if we had a negative power of a quotient. So remember, the negative exponent really kind of just told us to take the reciprocal. Well, if we have a quotient and we take the reciprocal, what was in the numerator goes to the denominator and vice versa. So, taking a look at the example that's presented here in the box, we have 2/3 being raised to the -4th. Well, look what that does. That basically just flips the base, which was 2/3. Now I flip it, makes it 3/2, and now my exponent is a +4. And then we can just go ahead and apply the rule just as we did in the prior examples, just distributing that 4 to the numerator and the denominator. And of course, here's the symbolic representation of that rule. And looking at it in terms of an example, so I have 2/3 being raised to the -2 power. Well, that's the same as saying 3/2 squared. And then that means I'm going to square the top and square the bottom, and that gives me 9/4 again. And what about example B? So this time, I also have some products going on. I have some products and quotients and negative exponents and all kinds of things. And so right away I thought, well, I'm just going to take care of this negative exponents. Rather than distributing a negative exponent to all these things, I'm going to go ahead and flip my base, making it now 4y over 3x, and then my power is positive. But then remember, what you have to do is apply that power to everything that's in the quotient. And since I have a product on the top and a product on the bottom, every one of these things is going to get that exponent of 3. So this really means 4 to the third, y to the third, and 3 to the third, x to the third on the bottom, which 4 to the third is 64. So that's 64y cubed over 9x cubed. And I don't believe there's any way to reduce that 64/9, so we are all set. That's our final answer on that. Okay, so we finally have reached our final exponent property, and this would be about rational exponents. So another way to say rational exponents, and we kind of think about it, they're really like fractional exponents. And so you may remember that when we talked in prior lessons and courses about fractional exponents, so for instance, if we have an exponent of like m over n, let's say it was 2 over 3, that the numerator had a special role, and so did the denominator. They had different roles. So the numerator actually told us to raise the base to a power, and the denominator actually told us to take a certain root, like a square root, a cube root, or whatever. So a fractional exponent actually is commanding us to do two different things. It's telling us to raise the base to the power and take the root. And as far as the order that you do that in, it really doesn't make a difference to your final outcome. You could take the base and raise it to the power and then take the root, but it's usually easier if you take the root of the base first, because then you're dealing with smaller numbers, and then raise that smaller number to the power. But the order really doesn't matter. And so, and also a way to kind of remember and keep straight which one's which is, I like to think about it like this, the higher power. And so I think about what's on the top is the power, it's higher power. And if we think about, where roots of trees and things grow, they grow underground. And so when we think about that denominator, we think roots grow underground. Now, if it turns out that the numerator is 1, so we're raising to the 1 power, then really all it's telling us to do is take a root. So if you're raising something, say, to the 1/2 power, that's just like saying take the square root. And if you're raising something to the 1/3 power, then that's saying take the cube root. But if you're raising something to, say, the 2/3 power, as I'm doing here in this example, it's really saying take the cube root of 8 and square it, or square 8 and then take the cube root of the result. And let's go ahead and turn the page and take a look at some examples of rational exponents. Now, for our examples purposes, we are going to do two different methods to write these expressions. in radical form, and but you can just choose whichever way you like best. But we're going to first, in method 1, we'll look at evaluating the root first, and in method 2, we'll evaluate the power first, and we'll see which one makes more sense to you and which you think is easiest. So if I had something like negative 32 raised to the 3/5 power, what that really means is, that my root is the 5, so I'm really taking the 5th root of negative 32, and then whatever I get, I'm cubing it. So this is the where I'm taking the root first. So when I take the 5th root of negative 32, and to take a 5th root in your calculator, and we'll talk more about this in class, but you can go under the math menu, and there is a key that allows you to tailor the root sign, the radical sign, to whatever root you want to take. And you do that by first typing in whatever number, so in this case it would be 5, and then going under math, and the nth root key, you'll hit the n where it's got a little n out in front and the radical sign, and then that will basically replace the n with the 5. So then it'll say like it's 5th root of negative 32, and it turns out that the 5th root of negative 32 is negative 2, and so this really means negative 2 to the 3rd power, which is negative 8. Now doing that with the power first, instead we would take the negative 32 and we would raise it to the 3rd power, and then whatever we'd get, we'd take the 5th root of. Now see, the challenge there is we're raising negative 32 to the 3rd power, which is going to make quite a, I guess not really a large number because it's negative, but a big number to work with. And so this really turns out to be the 5th root of negative 32,768. And so then the 5th root of that is, of course, negative 8. It's got to turn out the same as the other. So either way you went, you've got a negative 8 on that. So worked out the same. So we'll make this next example a you-try question, and you pick the way that you like the best. You pick the way, whether you want to take the root first or evaluate the power first, and I'll tell you what. For me, my example, I'm going to use method 1. So this is the one I'm going to use right here, but the final answer will be the same, so you choose either way that you'd like to do it. So pause the video now and write the expression 64 to the 3/2 in radical form, and then simplify it. Okay, so in this case, because the root was 2, that's what normally when we see the radical, we think square root. So unless there's a little number out in front of it, an index, that indicates otherwise, we automatically think of square root. Now if it helps you and you want to put the 2 out in front to remind you that you made the denominator the root, that's fine. It's just that in general that the radical without a number in front is the implied square root. So I took the square root first of 64 and I got 8. Of course it's also negative 8, but for this example we just went ahead and paid attention to the positive root, and then I raised that 8 to the 3rd, which is 512. And even if you did it the other way, you should have also gotten 512. Just dealing with much larger numbers on that one. So this is probably, method 1 is probably the preferred way. And finally, the last example will be looking at going the other direction. So what if we have something in radical form and we want to write it as a rational exponent? So remember how that works is we've got the power on the top and the root on the bottom. And so looking at example A, this would be the base, which is 13, raised to so the power is 4 and the root is 8. And because that exponent, 4/8 can be reduced, I'm going to reduce it to 13 to the 1/2 power. So that would be equivalent to that, but in reduced form. So hopefully you get the point of those, and I want you to try the next 2 as you try questions. So go ahead and pause the video and complete B and C, and then 2 back in to check your work. Okay, so in example B, when I was able to get this written as a rational exponent, I could reduce it actually to a whole number exponent. And so it turned out it was 13 cubed, which then I can simplify because 13 to the third power is not that large of a number. I just put it in my calculator and I got 2,197. Now in example C and also in example A, when we got to that final reduced form, we really couldn't simplify it without getting a decimal. So in C it turned out to be 5 to the 1/2 power, and really 1/2 means square root, but there is no nice integer value that's a square root of 5, so we would just leave it in this format. Well, that does it for today's lesson, so thanks for joining me in class.